Hello everyone, my name is Zhou Yixin and I am a PhD student at Jilin University. Now, I will be presenting our paper. First, let me give you a quick preview. The archaeological dating of bronze dings has played a critical role in the study of ancient Chinese history. Current archaeology depends on trained experts to carry out bronze dating, which is time-consuming and labor-intensive. In this study, we first collect a large-scale image dataset of bronze dings, which contains richer attribute information than other existing fine-grained datasets. Second, we introduce a multi-head classifier and a knowledge-guided relation graph to mine the relationship between attributes and the ding era. Third, we conduct comparison experiments with various existing methods, the results of which show that our dating method achieves a state-of-the-art performance. We hope that our work will enrich fine-grained classification research relevant to other interdisciplinary areas of expertise. Dings are cauldrons used for cooking, storage, and ritual offerings to gods or ancestors in ancient China, and they are the most important species used in Chinese ritual bronzes. The archaeological dating of dings has contributed to the study of ancient Chinese history. Although the excavated bronzes are massive, dating such artifacts depends on the long-term training and accumulation of expertise in archaeological typology. In addition, some artifacts are easy to identify to a precise age and others are difficult to identify. For the object, we focus on a ding, the features of which are similar and complicated in different eras, as shown in the columns of figure. The columns from left to right show some typical examples of Chinese bronze dings from 4 dynasties and 11 periods. The timeline under the image is the time range for the corresponding periods. We therefore consider this dating task as a fine-grained classification problem. Simultaneously, research into fine-grained classification is close to that of other areas of expertise because it often requires expensive specialized data and knowledge areas, such as birds and flowers. We collect more than 4,000 ding images from both 5 published archaeology books and 4 websites, and sort out 3,690 images as our dataset. Because many dating results are controversial, we re-argue the era of each artifact through discussions with 3 bronze experts. The collection and labeling of data were carried out by an archaeologist and 8 archaeology assists, who took approximately 8 months to complete. And the number of bronze dings in the Spring and Autumn and Warring States dynasties was much smaller than that in the Shang and Western Zhou dynasties. Each image is annotated with additional annotations, such as shape, characteristic and source. We also count the numbers of eras, shapes, and characteristic labels from different eras. To quantify the information provided by the additional annotations, we calculate the information gain of the shape and characteristic annotations of the era judgment, as shown in table. We find that the information gain in our dataset is more significant than that of the other datasets, which means that our shape and characteristic annotations provide richer information. Such information is therefore critical for improving the network performance. To address the challenges to our task, we construct a multi-head network for predicting the era of bronze dings on an archaeology knowledge-guided relation graph, as shown in the figure. The network consists of 3 parts, a multi-granularity module, knowledge extraction module, and archaeology knowledge-guided relation graph. The multi-granularity module is built to combine dynasty features with period features and enhance them interactively. After the backbone network, dynasty and period features are separately extracted by 2 heads consisting of 2 convolution layers and 2 fully connected layers. Then, in addition to applying an element-wise addition from dynasty head to period head to enrich period information, an element-wise gradient truncation addition is applied in reverse to enhance dynasty features without affecting the period performance. Because of the narrow interclass differences and wide intraclass variations of the bronze ding, archaeologists must combine various factors to determine the era to which they belong. We therefore introduce domain knowledge to improve the performance of the network, including the shape and characteristic annotations. We design a knowledge extraction module for extracting the shape and characteristic information of a bronze ding, which consists of 2 separate heads for extracting knowledge-specific features. Using the output of these 2 modules, we develop an archaeological knowledge-guided relation graph embedded with domain knowledge to enable the network to synthetically learn the era, shape, and characteristic labels. The nodes of the relation graph are the types of eras and attributes, and a set of directed edges and undirected edges are defined between these nodes. The two types of attributes have different effects on the dating by archaeologists. Based on this knowledge, we construct probabilistic classification losses to enable the network to learn information in the relation graph. To evaluate our method, we conducted comparison experiments on the proposed datasets. We compare our proposed network with other SOTA approaches under multi- and single granularity settings. Under a multi-granularity setting, we train all multi-granularity methods with two-level labels of the bronze ding datasets. Under a single granularity setting, we train all single granularity methods using fine-grained period labels of the bronze ding datasets. In addition to research related to fine-grained classification, we also compare our method with ConvenEXT, which is an extremely popular approach in traditional classification tasks. As table shows, using the same backbone ResNet 50, our method outperforms the state-of-the-art single granularity method P2PNet on the bronze ding dataset benchmark. And our method outperforms the state-of-the-art multi-granularity method HRN. Furthermore, we achieve the best performance for all 4 coarse-grained dynasties and 2 out of 11 fine-grained periods for each independent era classification. To demonstrate that our network can capture important regions of interest useful for bronze ding dating, we adopt GradCam for an intuitive visualization. For comparison, we also conduct the same visualization for the single granularity method P2PNet and the multi-granularity methods HRN and CHMCNN, which also exhibit competitive performances. Compared to the other methods, our network captures the key locations on a bronze ding when performing the dating, such as decorations and inscriptions. Our network is more concentrated within the discriminative regions of a bronze ding. In addition, we draw TSNE scatter plots from the learned high-dimensional period features of our network and some other comparison methods. For better visualization, we randomly select 40 images for each period. From the TSNE plots, we can clearly see that our network extracts more discriminative period representations of different images. In a future study, we plan to collect and open up more types of Chinese bronze data to facilitate research through learning-based methods. We hope that our study will provide further contributions to both the archaeological and deep learning communities. Thank you for listening to my presentation. If you have any questions or are interested in our research, please feel free to contact us.